Today we are going to discuss about multipole expansion. As you can see in the figure, there are two indices L and M, and for various value combinations of L and M, we are having different figures. Like for L is equal to 0, we have M is equal to 0, we have a single figure. For L is equal to 1, we have two orientations of M. For L is equal to 2, we have three orientations of M, and so on. The L is equal to 0 and M is equal to 0 represents a monopole. L is equal to 1 represents a dipole. L is equal to 2 represents a quadrupole and octopole and so on. So this is basically a simulation diagram, and the colors represents the intensity of the fields side. The multipole expansion. So basically what we want to do in this multipole expansion, that we want to have a single expression for a potential or the field or energy, and we from the respective terms we can get the respective potentials of monopole, quadrupole, dipole, etc. Like we have a general expression with some indices, and for respective value of indices we have a particular monopole or dipole that we will see later on. So multipoles are the poles resulting from a number of charges, and the potentials and electric fields can be expended in terms of multipoles. The energy of a charge system can also be expressed in terms of multipoles. As we know, the potential due to the some charge density can be expressed in terms of geometrical moments of the charge distribution known as multipole moments. The expression for the potential, the electrostatic potential, we already know. We can expand this divider 1 upon x minus x dash term in terms of Ligand polynomial. This expression has been derived in the book of Griffiths in chapter 3. Substituting this expansion into the formula for the static potential, we get this modified expression for the static potential. The Ligand polynomial multiplied by the density gives us multipole moments, which we denote by quantity small q, having indices small l and m respectively. So let us examine the dependence of the potential on the radial distance r, small r. So as you can see, this potential is varying inversely with L plus 1th power of R. So for monopole, like I said earlier, L is equal to 0. So if L is equal to 0, then this potential will vary as 1 upon R. This will give me a monopole. For dipole, L is equal to 1. In that case, the potential will vary as 1 upon R square. Similarly, for quadrupole, L is equal to 2 and the potential will vary as 1 upon R cube. Here you can view we mean by a monopole, a dipole, a quadrupole, and an octopole. The spherical multipole moments, like we defined in the previous expression, is a Ligand polynomial multiplied by the density and integrated over the space. So if we substitute the indices L is equal to 0 and M is equal to 0, the moment we get is for a multipole. If the indices are L is equal to 1 and for this L is equal to 1, three values of M are permissible. They are -1, 0 and 1, and these three denotes the dipole term. We can calculate the value of this quantity small q for these indices, like q for L is equal to 0, M is equal to 0 is this. And the value for Lagrange polynomial with the indices 0, 0 is 1 upon 4 pi, under root 4 pi. The value of the polynomial similarly for L is equal to 1, M is equal to 1 is under root 3 upon 8 pi. And the value of Lagrange polynomial for the indices 1, 0 is under root 3 by 8 pi. So we can calculate these multiple moments with these different indices. In Cartesian coordinate, we can use this expression, the Taylor expansion, and these identities, vector identities, A dot del and A dot del into A dot del. These two vector identities with this del and del by del xi. Together with these using these four vector identities, we can have this expression 1 upon x minus x dash. This is the Taylor expansion. On rearranging the terms, we arrive at this expression. And when we substitute the value of 1 upon x minus x dash in the expression for the static potential, we get the static potential as this expression, where the first term denotes the monopole, the second denotes the dipole, third denotes the octopole. And these multiple moments are always defined with respect to a point of reference. So what will be the point of reference? We see that if we take a reference point, x is equal to x0. So the value of the multiple moments depend upon the choice of the point of reference, although the sum of all multipole fields has the same value. If we consider the general case in which the point of reference x is equal to x0 is separate from the origin of the coordinates, the origin is denoted by x is equal to 0, the expression for 1 upon x minus x dash reduces to this expression. And when you substitute this in the expression for the potential and rearranging the terms, we arrive at this expression. The first term denotes the monopole, the second dipole, and the third quadrupole, and so on. We can calculate the electric field of the dipole using that potential we derived previously. And when you substitute the value of phi in this expression, we get the value of the electric field. The rearranging and using the vector identities, we arrive at this final term for the field. We can also calculate the energy of charge distribution using the expression. And we substitute the value of phi from the multipole expansion we have derived. This is the multipole expansion. We come across the expression for the energy. Here the first term is for monopole, the second for the dipole, and third for quadrupole. You can see the different notations. For monopole, we have used the expression, the notation is small q. For dipole moment, the standard notation is small p. For quadrupole, the standard notation is capital Q with indices ij. Molecular polarizability. In the presence of an external electric field, the electrons and ions in a molecule or atom will be slightly displaced. Their position is perturbed, and this displacement is in opposite directions from their mean equilibrium position. The molecule is thus polarized. The resulting dipole moment we calculate. The molecular electrons and ions are bound charges. When the charge is displaced from the equilibrium position x is equal to 0, it will be subjected to a restoring force, capital F. This restoring force is a combination of various forces. The first one is the force due to its equilibrium position. The second one is due to the natural frequency of oscillation. The third one is the nonlinear effects, and which are obviously small in magnitude. For the small displacement that is extending to zero and assuming an f and x are along the same line but in opposite directions, we have fx is equal to minus m omega 0 square x. Under the action of a static electric field, a charge will be displaced to a position x at which the restoring force equals the electric force. In that case, we can equate this force to the electric force EE. The dipole moment is defined as E into x, and we substitute this x from this equation, we get the dipole moment. We substitute this amplitude part, this constant part, as epsilon 0 gamma, where gamma is the polarizability in terms of E, epsilon, m, and omega. This polarizability is for a single charge with reference to another charge. For all the charges in the molecule, we have the dipole moment, the molecular dipole moment. And the polarizability here will be called molecular polarizability. The expression is the same, only the notations have been averaged to molecule. The dipole moment for a single charge as calculated above is with respect to the equilibrium position of the charge. Since different charges have different equilibrium positions, the dipole moments of individual charges in the expression are with respect to different reference points. Here we have taken the reference point as x is equal to x0. This will not cause any inconsistency for an equal amount of charges in the sum, in which case the monopole moment vanishes and hence the dipole moment of the molecule is independent of the reference point. For this reason, we will assume the dipole moment of the molecule to be contributed by an equal amount of charges in the molecule. If there is a net charge in the molecule, the net charge will be treated separately. The basis of these slides is chapter 4 of the book by Griffiths. The electric polarization is defined as the total dipole moment per unit volume and is given by the expression P, which is equal to the summation of the product of the number of the molecules into dipole moment of a single molecule. Now we divide the charge density in the medium into two categories: polarization charge density and the free charge density. The polarization charge density results from the polarization of equal amount of charges in each molecule, whereas the free charge density consists of a net molecular charge in the medium. So we can write the expression of the free density as. So this is the electric polarizability, and this leads to polarization of the medium. Polarization of the medium, that the charges are localized in the medium. We can find the charge density in a particular area of the medium, and accordingly we can proceed towards the dispersion and other characteristics of the medium. These are the references. The book by Griffiths, and the one is the book by Jackson, and the notes that are available on the internet. Thank you for your patience.